Thank you very much for the very kind introduction and opportunity to share what I'm doing and getting new knowledge, listening to other outstanding speakers. For me, eventful conference we all are attending this week is essential for international scientific communication and networking. At first, I hope everyone can hear me well. So that's right, thank you. I will try to keep my English straightforward during the whole presentation, even if I become nervous or overexcited. So my topic today is about optimization of isosurface rendering algorithm applied in medical imaging like computer tomography, MRI, and or any volumetric data. So I'm Daniil Savchuk. It's not working, I'm sorry. Yep. I'm Daniil Savchuk from St. Petersburg, Russia. I've been working at EPAM Systems for 2 years, and also I'm studying postgraduate at Peter the Great Polytechnic University for my PhD. I'm very glad to experience any collaboration and questions, so if you have any, please text me the email or Facebook. I will definitely answer you. When I prepared for the presentation, I thought about the outline, is it necessary or not, but watched out a couple of SPIE presentations I put it. However, you will know how it's long to get to the end. So for me, it's necessary to briefly cover the background of computer tomography and MR imaging to be sure that we have the same context. Using this background, I will say a bit about the general approaches rendering volumetric data, these advantages, disadvantages. After this, I will move on my own proposal, and for finalization, I will show the applications and results. So today is the St. Valentine's Day. I wish all you bad relations in your couples. So I don't know if housing league has been popular in the United States, but in Russia it was very popular. I even get known about the computer tomography watching the TV series 10 years ago when I was in school. And that time I figured out that computer tomography machine is Dr. House's favorite resting place. So I hope everyone basically know what does CT and MRI means. The set of images, of image layers where in every pixel the density of tissue is defined. So it's how every House MD episode started. It is mostly listed MRI layers, and if you put them into the stack, we can see that it was a human head. It's how we obtain the volumetric data from image layers set. So medical imaging uses a computer tomography and MRI imaging for diagnostics, for joint printing over 3D printers, like previous presentation. The data, the models for it prepared using the computer tomography and so on. What the problem is to extract the isosurface, visualize it, and what is crucial, to do it rapidly. But we set up the even more complicated goal. We wanted to implement the solution for WebGL, for web application, and in future for WebVR. We wanted to come up with ideas that will allow us to experience fully interactive visualization. So, however, the general approach that allows to do this is a ray casting method. By its own, the method is very simple. Imagine that you're sitting at your lovely working place, and from your eyes, from every screen pixel, we strike the ray that's going step by step into the surface, but until met into the space, until met the surface defined somewhere in this cube. On the plus side, the methods have the very high resulting image quality, but drawback is the low performance, because a huge amount of rays have to be traced and it takes too much time. The first idea optimizing this method is to bypass cases when rays have no any intersection with the object, but actually that's not enough. On the center of the slide you can see the abstract isosurface, and there are two general approaches that allow to optimize the rendering. The first one is a matching cube type of algorithms that approximate the isosurface by geometric primitives and perform the usual rendering after this. The second approach is a KD3 method that defined the tree topology in the space that allow to faster performance the ray tracing. But anyway, both of these general approaches requires the preprocessing of data and couldn't apply for fully interactive isosurface level changes. But it's what we have done. The proposed method acceleration is based on two-step strategy. The both steps are performing on each render frame. On the first step, we're rendering the low-resolution texture that have significantly less rays to be traced. And we store the information about distances and colors to the isosurface to use this information on the second step, where we calculate the high resulting image quality. And so, how does it work? So this in our eye, we are looking to the screen and trying to visualize the object. As we remember, we strike the ray through every screen pixel, and it takes too much time. But actually, if we reduce the ray count on the first stage, we can significantly faster perform the first stage. And using the information about the distances to the neighboring voxels, we can significantly shorten the tracing distance. And even if colors of neighboring voxels are close, we could approximate the resulting color without performing the ray tracing at this point. This is very interesting because it almost doesn't take any time to perform the second stage, but always the corner cases appear. It is my grandma on the right. Yeah, my grandma always makes corrections, and she has donated her CT data to the science, and actually I hope she doesn't see this because in life she's a bit more handsome. There are three typical cases when we have to use an exception. The first one is when the surface doesn't lie between the neighboring pixels as it was presented on the previous slide. In this case, we have to right-select the tracing direction. How do we do this? We compare the transfer function gradient value, and if it's positive, we're tracing forward another backward direction. So the second and third cases appears when we touch the border of isosurface. In such cases, we have to fully trace the ray because we don't know where the surface exactly. Fortunately, such cases doesn't appear too frequently. It's about 5% of voxels in this example. It's outlined by red and green lines. As we remember, as we talked before, the lower resolution of the texture in the first stage, the higher general acceleration. But we can't reduce the texture size all the time because as a reduced factor about 4 or 5, we start to experience artifacts because of missing borders or details. So actually, for this proposal, reduced factor 2, 3 is experimentally optimal. So described approach has already been used in many applications. So one of them you can try using the link presented in the slide. It's our Web 3D DICOM viewer, first in the world Web 3D volumetric data visualizer. It becomes possible only with this proposal because my grandmother watching you. Because all other approaches requires complicated computations on GPU or CPU that doesn't support it by WebGL properly. And of course, we have tested the solution for HTC Vive because up to me, virtual reality is a big opportunity to improve human perception. So the implemented algorithm allows to experience fully interactive visualization is about 70 frames per second per each eye. In my opinion, such solutions could be useful for doctors who are trying to explain their patient what's happening with them exactly. Such experiences allow us to achieve the better understanding. And so what's going on in the video? Just now I selected the brainstem region and a few other useful regions, and it's perfect because I can be 100% be sure where every region is placed if I would like to study it. And so let me move to the digits about the results. So, and here is a first step texture size reduced factor, and the better acceleration has been achieved at the second example when we tried to visualize two isosurfaces at one time, one of them semi-transparent, and the worst acceleration has been achieved on the fourth example because a lot of little details there. For instance, the long tubes that leads a lot of rays to be fully traced. To outline the results, I would like to say that we have significantly shortened the tracing distance we increased the rendering speed up to 4 times, and our method keep the higher image resulting quality at all. The main advantage of our algorithm is an ability to be composed with other optimizations, for instance with KD3. So for the finish, I would like to say about 2 other our open source projects. So one of them is a protein and molecular web visualizer that allow to render large PDB files even in VR mode, even in mobile devices. So right now I'm discovering the HIV protease blockade with ligand. And so the second project is a NGB web genome browser that allows to stream and manipulate huge amount of data like 500 gigabytes of DNA sequences. So I have a flyers with detailed information about these projects. So I'm looking forward to answer the question about them after the presentation. So, and it was an outstanding pleasure for me to presenting you my research. So thank you very much.